Gabrielle Taylor. I'm going to be doing homework 1, Part B, Part 1. So it says that there are going to be 3 identical tanks with a cross-sectional area of 1.2 meters squared. And they're going to have a bottom drainage hole area of 0.2 meters squared. The drain will sequentially in series, and then the flow of the first tank is maintained at 0.5 meters cubed per second until the system eventually reaches steady state in which the flow of the first tank is increased by 10%. Simulate the liquid level of these tanks as a function of time. So the first thing that we want to do is let's draw what is happening. So you have a tank, you have a Q in, this has a cross-sectional area, and this has a certain height of a liquid level as well. And then you have a drainage hole here. Then you have another tank with some height. I'll do that height 2, height 1, and drainage here. And then you have a third tank as well with a height of 3 and a drainage hole. So this is going to be flowing into the first tank is going to be a Q in, so our flow rate going into the first tank. And then we're having a Q leaving that tank, right, that drainage hole, which is going to be a Q1. So that's going to be feeding the second tank, and then you're going to have a Q2 here. So that's leaving the second tank, and it's going to be filling the third tank, and then you have a Q3 finally. So pretty much what we want to simulate is there's going to be a change in volume, right? We want to know what the change in volume of each tank is, and then all the tanks together. So pretty much we have is dV, so our volume of time, minus our Q in, Q out, right? So our volume can be represented as not just our volume, but our cross-sectional area times our height, right? So one thing that we know about this problem is with each of these tanks, none of their cross-sectional area is changing. The only thing that's changing in respect to time is your height. So we can change that as cross-sectional area of the entire tank, and then the change in height with the change in time is equal to Q in. So we have our Q in, we don't have our Q out currently, right? So this has a cross-sectional area right here, and they all have a cross-sectional area, right, of these drainage tanks. So what we can do to figure out what the flow rate coming out of these tanks is we can use Bernoulli's equation, right? We have a flow rate going out, and we have pressures and velocities, right? So to figure out what we need currently is we're going to need to find the velocity of the liquid flow coming out of the drainage hole of these tanks, right? And they should have the same equation, but they're going to have different answers depending on the heights. So let's figure out what that equation is. So using Bernoulli's equation, we can use P2 minus P1 over density plus, then you have G, which is your gravity, minus Z2 Z1. And then you have your velocities. So you have, this one is 1. So velocity 1 squared minus V2 squared over 2. Right. And so when we think about these tanks, they are both open to the top, and this one is open at that drainage hole to the environment. So that means they are both going to have 1 atmosphere of pressure or atmosphere of pressure. So their pressures will be equal to each other. There's not a significant difference. So that will be a 0 because you'll be subtracting that. And then we will look at these two. So we're saying that we are doing 2 different from the liquid level. So where is it coming from? So it's saying from the bottom of the liquid level to the top of the liquid level, right? So what is that going to give you? That's going to give you your height, right? So that's going to give you your height. Now, when we think about this equation, we're thinking about it in the way of gravity. Gravity could be either a minus or a plus, depending on which direction you put it in. So if we want to keep this as a positive, it will be in the down position. But if that's in the down position, then your height will be negative. So we're going to change this to GH. And then we're going to move this over to the other side because we're trying to solve for a velocity, the second velocity. So v1 squared minus v2 squared. Okay, and so this isn't the q, what it's asking for this velocity. It's asking for the change in velocity at the top of that liquid level, right? And so at that liquid level, the velocity isn't changing negligibly, right? So it's not going to have a big enough velocity so that we can bring that to 0. So now we have is GH equal to v squared v2, and then we have this, your two negatives are going to cancel out, and then you're going to have is v2 is equal to the square root of 2gh, right? And so when we think about that, so that's just our velocity, so it's just a one direction. We also have to think about the flow of the size of the flow itself, so the cross-sectional area of that flow that's leaving the tank, right? So here, I'll just write it here, right here. So you have the cross-sectional area out leaving the tank, and then you have 2gh. And then this is going to give you your equation that we're going to use, right? So we're using that. And then you can actually just divide for your area and then just have that under there. So that's what we're going to be doing. So I'll just rewrite this right here. So, and then we can even use this for, so I'll write this for what we're going to be doing for each tank. So height 1, that's height 1 there. This is the change in height 1. Change in height 2 is going to be, and I can even write this as just Q1, and that'll be Q1 minus Q2. And then height 3 is going to be Q3, Q1, Q2 minus Q3.
Real Taylor, I'm going to be doing homework 1 part B. I'm doing the coding portion of it, and so pretty much what the statement says is we have the cross-sectional area of 1.2 meters squared. We have our drainage hole of 0.2. We have 3 tanks in series, and then we have initial steady state of Qn at 0.5 meters cubed per second. And then that flow is going to increase after that steady state by 10% in the Qn. So let's code this. So the first thing we want to do is import numpy as MP, and then from scipy.integrate, we are going to import, I spelled that wrong, integrate, we're going to import solve IDP, and then from plotly.subplots, we are going to import make subplots. Okay, shift enter. Shift enter. Okay, so after this we can do our initials. So our cross-sectional area of all 3 tanks is going to be 1.2, and then we have our A out is going to be 0.2, and then we have our gravity, which is 9.81. And then what we want to do is we have our Qn at steady state, so not the current one we're going to have. So is at steady state is going to be equal to 0.5. And then from this, we know that we're going to have our height at steady state. And this is going to be equal to A out minus our Qn at steady state squared divided by 2 times G. Okay, and then so after that, what we're going to do is define our right-hand side of the equation that we already derived. So that is going to be define right-hand side, and we are going to be doing time and then a vector. and then we're going to unpack that vector. So we want to solve for height 1, height 2, height 3, right? And that's going to be in that vector. So what else do we know about this problem is that from that steady state, we're going to increase by 10% of that flow rate. So Qn is equal to Qn steady state times 1.1, and that's going to give us a 10% increase. And so now what we want to do is we're going to want to solve for the heights. So we need to do our Q flow rates, right? So Q1, Q2, Q3. Because these are going to give us what we want. So on the board, we had said that our first one is Q in minus our first steady state. So that's A out times NP dot square root of G times your, oh sorry, actually 2 times G times your height. And this is height 1 because this is the first tank. So then after that, we're going to have is our Q, not our Qn, it's going to be, yeah, it's going to be a Qn. Qn, well, Q1 minus A out times NP dot square root times 2 times G times 2. And then we have Q2 minus okay, so that is our Q, and now what are we going to return from this? What we want to return is our differential change no. Okay, so thinking about this, it just doesn't make logical sense that I'm doing that. What I think I need to do is not have these QNs. Doesn't make sense. So take these out. Yeah, this makes more sense because we're solving for our Qs that are leaving our tank, so that wouldn't make sense. It just needs to be like this. Because if we're subtracting those two, that would be similar to what the differential height would be due to time, but we're not doing that right now because what we're going to return is the heights, right? So since these heights are going to give us 3, we need to do NP.array because it's going to give us an array. And then from that, we're going to have to put it in brackets. So now we know is our Qn, right? The first one, Qn minus, yeah, let me put these also in parentheses. So Qn minus Q1 divided by our area, right? Then we have our Q1 minus our Q2 divided by our area, and then we have Q2 minus our Q3 divided by our area. Okay, so shift enter. Okay, next thing that we want to do is we are going to try to solve for our solve IDP function, and so we need a t end. So we're just going to give t end equal to 20, and not like that. And so our solve IVP function, so let's say resolution, res solve IVP, initial value problem. So we first need to give it the thing we want to solve, which is our right-hand side. Then we need to give us what our time length is, so 0 to t end. And then from that, we are going to have our height at steady state. And so our height at steady state, we have 3 things that we want to solve. So we have this initial value. So it's trying to make us have our initial guess of that, right? So if we just use this, it is not going to give us, it's going to give us an error because you need 3 separate things. This is an array of 1 by 3. So we need to make this an array of 1 by 3. So we need to do some scalar multiplication. So we're going to have to multiply by 3. So it's going to give us a guess of the height at steady state for all 3 tanks is your guess. Next, so we have dense underscore output is going to equal true. And needs to go like that, true. And then method is going to be equal to redo. And, yeah. Okay, so after that, let's make our plots. So the first thing that we want to do is our t-plot. So our t-plot is going to give us a time plot. So for a time plot, we want to do np.line space, right? And so this is going to give us from 0 to t end. And that's going to give us values from 0 to 20, which is our t end. And we want to separate that and split it into how many increments? 100. So that's going to be our time graph. So now we need to use our resolution to solve for it. So we have height 1, height 2, height 3, right? So now we need to solve for it. So res.solve, and then we're going to use our time plot for that. And then after that, we can now make our subplots. So fig that equal make underscore subplots. And we don't have to do anything crazy with that. And then fig dot add underscore scatter. So our x is going to equal our t-plot, and our y for the first graph is going to be h1, name is equal to h1, and then node is equal to x. Okay, I'm just going to copy and paste this and then just change the heights, which you'll see. To okay. Then here. Okay, now let's just do our fig dot add fig update. So our width is going to equal 600. Our height is going to equal 400. And that needs to be an underscore there. Okay, let's see. No, that's not correct. Okay. What could be wrong? That's it, yeah. That's correct. That's correct. That's correct. That's correct. Okay, so it's probably this height right here. There you go. Okay, so I just need to add this parentheses right there. So now we have our lines here. So we can see that it's coming to a steady state around 4, right? It's pretty close to 4 on both. So you can see that 1 kind of shoots up faster after that 10% increase, and then 2 and then 3 comes pretty evenly, and then they all kind of are around this 0.35 range of height. So that is the end of homework 1 part B1. So before we move on to part B2, I wanted to clarify a problem in the code. So I had 8 out minus Q in at steady state. That's incorrect. It's actually Q in for this height steady state. It should be Q in steady state divided by your cross-sectional area leaving the tank. And that's squared divided by 2GH, right? That's what we derived in our equation. So that is going to fix this plot. So let's look at this plot. So this is going up to like 3.8, right? Which is what we want. We wanted it to kind of curve to 3.8. So after this, let's move on to part 2. So part 2 of B says 3 tanks in a series of in part B1 is equipped with a proportional controller that adjusts the flow of the first tank to control the liquid level of the third tank, right? And so at times equals 0, there's a set point of the third tank is 10% higher than the original steady state height. We're going to simulate the response of the different values of the controller, and we're going to try different controller values of the controller gain, which is KC. So 0 0.1, 1, 3, 5, 6, and 7, and we're going to comment on the impact of that controller gain, right? So let's look at this. So we want to have it be the third tank's set point to be 10% higher than the steady state heights. And this steady state heights is our all 3 tanks, right? So what we could do is height 3 set point, right? And that's just going to be the height of the steady state times 1.1, right? Because that's going to give us what we want. So now that we have our height set point, what we need to do is our KC value. This is our controller gain. This is going to help us. This is going to help control how much that controller is going to move, right? So that's going to be 0.1. We'll start out with 0.1 and then we'll move it up. Okay, so the next thing that we want to do after we have this controller gain and we want to know our set height, we actually have to change this Q in right here. Because we said that the flow rate going into the tank is depending on that height set point, right? We are wanting to change that height set point based on that flow rate. So we're going to change that flow rate depending on how far away, that height of the third tank is to the actual height of the set point, right? So if there's a bigger difference, we're going to have that controller gain is going to be multiplied by a bigger number. And so that's going to be we're going to put more flow into it, right? So to do that, we're going to change this equation. Since we want this to be bigger, what we're going to do is our KC is just how much that is going to be moved, right? That controller gain is how much that is going to add to that flow rate. So KC, and then what we want is we are going to do the height 3 set point minus the height 3. Okay. And then we're going to change the time to see this gradually get bigger. We're going to need to do 100 instead for the TN. So let's see what this does. Okay, so this is 0.1. And you can see that we are just hitting it up. There's a little big fluctuation up here, and then it's going right? So, okay. There's nothing crazy with that, right? So let's change this to, I think, 1 was the next one. Shift enter. Let's see. Okay, so you can see there's some waves in there, in the waves. So this isn't really getting consistent. So we're actually kind of overshooting these tanks if you look at it. We're going above and wiggling out. So let's hit another one. Let's say, I think the next one is 3, and 5. 3. 3 is crazy. I mean, you can see that it's gradually getting more variable. It's getting variety. It's getting bigger. There's bigger jumps between this. So let's say 5. Okay, so you see it's getting gradually bigger. These waves are getting gradually bigger. But you're still having all these squiggle marks. It is not getting a consistent flow no matter what your time is, and it's overshooting and undershooting. Okay, let's try 6. Okay, so this is just very inconsistent. It has an inconsistency on all these times. It's not lessening like the other ones was. This is consistently, varied. And they have a lot of variables in this. So let's try 7. Oh, so 7. Let's look at the 7. I got an error, which is interesting because this was working when we had 6 and all those other numbers, right? So what's the problem with this? It says that infinite in mass, which means that there is too many numbers. There's an infinite amount of numbers, right? So what's happening is it's practically crashing it. So this cannot be a 7. There's too much of that with it. So what's pretty much saying is, you can go to 0.1 as a KC, as your controller gain, and you can have your consistent one. So it really depends on your controller gain of how stable your flows are going to be and how stable those heights are going to be as well. So that's the end of homework part B. Thank you.